Welcome to The Explainer. Today, we're tackling a massive, insidious trap that almost everyone falls into when building data models, and that is handling imbalanced data. Seriously, if you've ever built a classification model, celebrated a nearly perfect accuracy score, and then found out it's completely useless in the real world, well, you're in the right place. Okay, let's dive into this.
Take a look at the reality of the data we deal with literally every single day. Whether you're looking at manufacturing defects at 0.5%, disease diagnoses at 1%, or network intrusions at a tiny fraction of a percent, the vast majority of your data is just normal. It's the classic needle in a haystack problem. Your data is 99.9% hay, but the entire reason your model even exists is to find that microscopic sliver of a needle, the fraud, the disease, the defect. And usually, the more consequential the minority class is, the rarer it tends to be.
So, picture this. You build a brand new fraud detection model. You run your tests, and it comes back with a brilliant A+ grade, 99.9% accuracy. You pop the champagne, you celebrate with the team, and then you deploy it, and you drop the bombshell. The model is entirely, completely useless. Why? Because it achieves that 99.9% accuracy by predicting not fraud for every single transaction 100% of the time.
Now, I want you to really think about this intellectual mystery for a second. Why on earth does a 99.9% accurate model catch absolutely zero fraud? The secret here is that the model isn't actually broken. It's doing exactly what you told it to do. It's behaving entirely rationally. The model learns that always guessing the majority class, just assuming everything is normal, hey, is literally the laziest, most efficient way to minimize its overall error. It's technically correct, but again, completely useless for what we actually need it to do.
Now, what's really interesting about this slide is the math behind the solution. Here's a standard confusion matrix for 1,000 samples where 990 are negative and only 10 are positive. If your model just constantly predicts negative, look at that bottom row. You get 992 negatives correct. Great, right? But look at the top row. 0 true positives, 10 false negatives. You caught exactly 0 actual positive cases, 0 fraud, 0 disease. But because you got the 990 boring cases right, the formula happily spits out a 99.0% accuracy. This brilliantly illustrates exactly why accuracy is a dangerous lie, when one class has way more samples than the other.
So how do we actually fix this? Well, here is our roadmap for today. First, better metrics for rare events. Second, changing the data with SMOTE. Third, changing rules with weights and thresholds. And finally, putting it together in the imbalanced data pipeline.
All right, let's jump straight into Section 1, better metrics for rare events, because we really need to start measuring what matters.
Look, before we can even attempt to fix the model, we absolutely must fix how we measure its success. First up is precision. Precision asks a very specific, simple question. Of everything your model flagged as positive, how many actually are positive? It's basically about making sure that when the alarm bells ring, there's an actual fire. High precision means very few false alarms. You aren't waking everyone up in the middle of the night just because someone burnt a piece of toast in the break room.
Then we have recall. Now, recall is your ultimate needle finder metric. It asks, of everything that is actually positive out there in the real world, how many did we manage to catch? High recall means you have very few missed positives. You're making sure you don't let a single bad guy slip through the cracks, even if it means you end up checking a few innocent people along the way.
So the crucial takeaway here is understanding the dynamic between these two. It's the classic precision-recall trade-off where people will often tell you, hey, you just can't have both. Think about it. If you cast a massive, super wide net to catch absolutely every single needle, giving you high recall, you're inevitably going to pull in more hay, dropping your precision. But if you want to be absolutely 100% sure you only catch needles, your net has to be so tiny that you might miss some, which drops your recall.
And that brings us to the F1 score. The F1 score is the harmonic mean of precision and recall. It acts as the ultimate balancer because it severely penalizes extreme imbalances between the two. You can't just game the system anymore by maximizing one at the total expense of the other. And actually, if you have a specific use case, like fraud detection, where missing fraud is way worse than a false alarm, you can use its cousin, the F-beta score, like F2, to basically tell the model, hey, recall matters a bit more here. Oh, and for that completely useless model we talked about that always predicts negative, its F1 score is a flat 0. That tells you the truth right away. Another fantastic alternative is the Matthews Correlation Coefficient, or MCC. I like to think of this as the balanced metric. It ranges from -1 to +1. And here's the kicker. It only gives you a high score when the model genuinely performs well on both the majority and the minority classes. It takes the entire confusion matrix into account, staying perfectly balanced even when your class sizes are wildly, radically different.
Moving right along to Section 2, changing the data using SMOTE.
So if the data is incredibly skewed, what if we just fundamentally alter the dataset itself? And this brilliantly illustrates how clever data science can be. Enter SMOTE, which stands for Synthetic Minority Oversampling Technique. Instead of just lazily copying and duplicating existing minority samples, which, let's be real, easily causes your model to overfit, SMOTE creates plausible, brand new synthetic minority samples. It actually interpolates. First, it finds a minority sample's nearest minority neighbors. Second, it picks one of those neighbors at random. And third, it literally draws a line between them and creates a fresh, mathematically sound new sample right on that line segment. You get brand new data right in the same region.
Let's quickly look at the trade-offs for these sampling strategies. Random oversampling, it simply duplicates the minority. It's super simple, but you definitely risk overfitting. Undersampling, it removes minority samples to match the minority count. Sure, it's fast, but you suffer from information loss because you're basically throwing away perfectly useful data. SMOTE adds synthetic minority data. It reduces overfitting, and yeah, while it does have a slight risk of creating a bit of boundary noise, it's very often the gold standard when you have a moderate imbalance and enough minority samples to make it work. All right, let's jump to Section 3, changing rules with weights and thresholds.
But what if you really don't want to mess with the dataset itself? Well, let's talk about changing the rules of the game during training. Enter class weights. Instead of uniform rules, we can assign a higher weight to misclassifying the minority class. Let's use a specific example to make this concrete. Say you have 950 negative samples and 50 positive samples. By calculating the class weights, you can actually mathematically force the model to pay 19 times more attention to that positive class. Literally misclassifying one single positive sample will cost the model as much as misclassifying 19 negative ones. This forces the model to care about the rare stuff without creating any new data points.
Then we have threshold tuning. Most classifiers output a probability, right? And the default threshold to declare something positive is usually 0.5. But guys, 0.5 is a completely arbitrary number. Let's demystify moving this decision boundary. If your model sees a fraudulent transaction and says, I'm 15% sure this is fraud, a 0.5 cutoff completely ignores it, flags it as not fraud. But if you tune your threshold down to 0.10, suddenly, boom, you catch the fraudster. As long as fraud gets consistently higher probabilities than non-fraud, there's always a threshold that separates them.
Building on this idea, we can implement cost-sensitive learning. This takes everything out of the abstract and places it squarely in the real world, because we all know different mistakes cost different amounts. Look at this matrix. If you miss a fraudulent transaction, a false negative, maybe that cost your company 10 grand. So we assigned it a cost of 100. If you falsely flag a normal transaction, a false positive, maybe you just mildly annoy a customer with an extra verification text. We assign that a cost of 1. By incorporating real-world misclassification costs, your model starts optimizing for total cost savings, not just some abstract error count. It's honestly the most principled approach you can take.
Let's move to our final segment and see how this all builds into Section 4, the imbalanced data pipeline. You see, fixing class imbalance isn't about finding one single magic trick. It's about building a cohesive strategy. So here's your checklist, your ultimate pipeline for tackling skewed datasets. Step 1, ditch accuracy immediately and evaluate using F1, AUPRC, or MCC. Step 2, evaluate if you need to use SMOTE to synthetically boost your minority data to give the model more examples to learn from. Step 3, apply class weights to heavily penalize those rare mistakes. Step 4, always tune your probability thresholds to optimize for your specific metric instead of just settling for the default 0.5. And finally, implement cost-sensitive learning to tie your model's performance directly to actual real-world impact. I'm going to leave you with this provocative thought as you go back to look at your own datasets today. Take a really close look at that high score you've been celebrating. Ask yourself, is your model actually accurate, or is it just lazily guessing the majority? Well, now you have the exact technical toolkit to find out, and more importantly, to fix it. Thanks for joining me on this explainer, and I'll see you next time.